Aloha! In this second lecture of our Acids and Bases series, we discuss strong versus weak acids and the concept of pH. Let's begin with strong versus weak, and first recall what an acid is. An acid, according to Arrhenius, is a substance that increases proton concentration in water. So acid molecules have to have hydrogen atoms, and when they dissolve in water, those hydrogen atoms become separated from the molecule as a proton. Acids can be divided into two main categories, strong and weak. Strong acids are the ones that fully dissociate in water, and what we mean by that is if 100 molecules of a strong acid dissolve in water, every one of them becomes separated from its proton. So full dissociation. There are 6 strong acids, and I've listed them here, although I have seen a list of 7 somewhere else, and I wondered where that 7th one came from. I found it, and I disagree. I think that 7th one is a weak acid. So in the next video, I think we'll mention what that 7th one is. So the 6 strong acids, here they are, and these are some of their uses. Hydrochloric acid is found in gastric juice, so it helps with food digestion. Its formula is HCl. So HCl, when dissolved in aqueous solution, fully dissociates into the protons and the chloride minus anions. These are the conjugate base anions of HCl. The full dissociation is acknowledged by this one-way arrow here. If you visualize hydrochloric acid in solution, it might look something like this, where all of the protons are separated from the chloride anions. There are no molecules here. All of it has been dissociated, full dissociation. Hydrobromic acid is used in organic synthetic reactions. So it's used to build organic substances, and it's used quite a bit. The chemical equation describing its dissociation is similar. Hydrochloric acid, I associate that with the state of Hawaii because, after all, it does have the symbol HI, and I live in Hawaii. So I like to think of this as Hawaii's state molecule. So if I had the rights to edit the Wikipedia page, I would list the state molecule right below the state flower of hibiscus. So anyway, hydrochloric acid is actually used for other things. One of them is the substance is flagged by the Food and Drug Administration because it's a precursor to making methamphetamines. So if you have any hydrochloric acid in your garage or something, you might have some interested parties coming and knocking at your door soon. The chemical equation describing the dissociation is similar. All the strong acids have similar chemical equations, one-way arrows. They all dissociate. Now the first 3 are binary, meaning hydrogen and one other element. These are the halogens. The next 3 strong acids, the conjugate base anions, are oxyanions. The first one is nitric acid, which is used in fertilizer. Nitric acid, when it reacts with ammonia, forms ammonium nitrate, which can be used as fertilizer. So this stuff helps feed people. The formula for nitric acid is HNO3. In an aqueous solution, it fully dissociates into the protons and the nitrate anions. You can visualize nitric acid right here. All of the protons are separated from the nitrate anions. Again, no molecules dissolved. They're all dissociated into their protons and anions because it's a strong acid. Perchloric acid is used in rocket fuel. Here's its chemical equation of dissociation. Sulfuric acid is used in lead-acid batteries for a long time now, since the 1800s. And sulfuric acid is actually a diprotic acid. It has the ability to release 2 protons per molecule, but it's only the first proton which comes off fully. So every molecule releases its first proton. So there is the proton, and the conjugate base is that bisulfate anion. Now, bisulfate still has a proton that it can release, and it does so, but only weakly. So this acts as a weak acid. Only a fraction of those particles will release their protons. That's the difference between strong and weak acids. Strong acids are fully dissociated, and weak acids partially dissociate. There are 6 strong acids, but there are many more weak acids. So let's take a look at just a few of them. Now, strong versus weak, the difference is the extent of dissociation, not their ability to burn you. They will both burn you if they're concentrated enough. So don't have that misconception. You don't want to mess around with some of these weak acids just because you think they're not dangerous. They're very dangerous. Hydrofluoric acid, this substance can be used to dissolve glass. And if you have, say, a chemical laboratory where you perform nasty chemical reactions, you want to clean out that glassware really well, you can just swish a little bit of hydrofluoric acid in there, and it'll get rid of all the gunk, as well as trim off a little layer of the glass while it's at it. So after you wash your glassware, your glassware weighs a little bit less than it did before. So I guess you can only do that so many times. I heard a professor at Manoa does that. University of Hawaii Manoa uses HF. So here's the formula for HF. This is a weak acid, and we acknowledge that by the two-way arrow, which represents the equilibrium between the undissociated HF molecules and the dissociated particles, the protons and the fluoride minus anions. You can visualize what HF might look like in solution right here. So there are a few protons and fluoride minus anions, but the majority of the hydrofluoric acid is dissolved as molecules. So only a fraction of them dissociate. It's partial dissociation. I used to think it was about 1 out of 100 molecules dissociate, but before doing this lecture, I checked my facts, and it turns out it's 1 out of every 12 dissociate. So I had to cross that out. Pardon me. I hope that I haven't caused any problems in anyone's career, because I've taught that it's 1 out of every 100. Now, the HF dissociation, which is written right here, can also be written right there. If you remember, protons in solution are always close to a nearby water molecule, and you can write a proton as H3O+ to acknowledge that. So this chemical equation can be rewritten including the water molecule. So when HF splits apart, that proton combines with the water molecule to form the H3O+ and the fluoride minus. So these two chemical equations are showing you the same thing. Acetic acid is found in vinegar. Vinegar is usually 3% of it is acetic acid. I think it's 3% by mass, but it could be by volume, I'm not sure. Acetic acid is CH3COOH. So lots of hydrogens in here, but it's this one right there that's attached to oxygen that dissociates from the molecule. Those are attached to carbon, and they do not like to separate from carbon. Hydrogens that are attached to oxygen are easier to separate. So this will dissociate, and about 1 out of every 75 molecules dissociates. So in that respect, acetic acid is weaker than hydrofluoric acid, because only 1 out of every 75 give you protons. The more protons, the stronger the acid. Nitrous acid is used in food preservation as a meat preservative. because this helps make sodium nitrite. And sodium nitrite is found in Spam. Lots of Spam here in Hawaii, by the way. People buy that stuff up. And if you look at a can of Spam, look at the ingredients, you'll see sodium nitrite on the back. Also, your Pepperidge Farms sausages got it. All kinds of meats have it. So nitrous acid is HNO2, and in solution, this dissociates to give you the proton and that nitrite, conjugate base anion, and about 1 out of every 15 molecules dissociates. Phosphoric acid is found in soda. This is a triprotic acid, so it can give 3 protons. Now, the first one, comes off a little bit easier. The next one would be more difficult, and that third one would be even more difficult. But the molecules, about 1 out of every 4 molecules release the first proton. Now, the conjugate base is the dihydrogen phosphate, and this can act as a weak acid by dissociating further, but the ratio would be less. It would be like 1 out of every 100 or so. So I don't know what the ratio is, but it would be less than 1 in 4. So H2PO4, you can find that in the form of sodium dihydrogen phosphate. So this ionic compound right here provides H2PO4. So if you have this in solution, of course, this will fully dissociate because it's ionic. So you get your metal cation and the anion right there, but that anion acts as a weak acid. So there's the equilibrium arrow. So you get a fraction of protons coming off, and the HPO4 minus 2 ions, and it looks like 1 out of every 1300. Wow. So I had it way off. Not 1 out of every 100. Sodium dihydrogen phosphate is used in food as a thickener and emulsifier. So that's some weak acids. There are many, many more, thousands probably. I'm not sure. I've never seen a list. But 6 strong acids. You should memorize those, and you should probably memorize a few of the more common weak acids. Now, the strength of an acid depends on which acid it is you're talking about, the identity of the acid. In other words, what is the molecule? Okay, what is the structure of the molecule? And its concentration. So both of these determine how strong the acid is. Now, by acid strength, we mean how much proton concentration is there. So both of these will determine the proton molarity. If you know what the acid substance is and you know what its concentration is, you can actually calculate the molarity of the protons that you'll find in solution. And we'll spend a lot of time doing this in this chapter. Given the identity of the acid and its concentration, you'll be asked to calculate the proton concentration. That's the big question in the acid and base chapter in your Gen Chem text. Okay, given a solution, find the proton molarity. And molarity is represented by brackets here. So what is the proton molarity? Let's do an example of such a calculation. Suppose you are asked to determine the molarity of proton in a solution made by dissolving 0.015 moles of HCl in 1 liter of aqueous solution. Now HCl, if you go back to your list of strong acids, you'll see that it's the first one on the list. This is a strong acid. So when you mix 0.015 moles of HCl in 1 liter of solution, the molarity of the HCl that you're initially making is calculated as moles over volume, 0.015 over 1. So the molarity of HCl is 0.015 molarity. Now, every molecule of HCl dissociates into protons and chloride minuses. And if you make 0.015 molarity of HCl, because all of this is now in the form of dissolved protons and dissolved chloride minuses, you end up with 0.015 molarity of protons. So that's the answer right there. 0.015 molarity is the proton concentration. Now I've written the pH right below it. The pH is 1.82. And we'll see here shortly that if you know the proton concentration, you automatically can quickly calculate its pH. So when the proton concentration is 0.015, that means the pH is 1.82. We'll see that equation which lets you calculate pH from proton concentration here in just a second. First, one more example. Determine the proton concentration if 7.31 milligrams of HCl dissolves in 25 milliliters of aqueous solution. This one's a little more tricky because you're not told how many moles and you're not told how many liters. It tells you how much mass is dissolved, and it's in 25 milliliters. So it takes a little bit of work to figure out what the molarity of HCl is. So the molarity of HCl is moles over volume. So we need to find moles of HCl. So you take that 7.31 milligrams of HCl, convert milligrams to grams, and then convert grams to moles. 1 mole of HCl is 36.46 grams. Now, I'll remind you how to get that molar mass for HCl. If we jump over here to our periodic table, you look up the atomic mass of hydrogen right there. Okay, the atomic mass of hydrogen is about 1.01, and then go over to chlorine. The atomic mass of chlorine is about 35.45. So 1.01 plus 35.45 is 36.46. So that's how you get those molar masses again. You probably remember that. So here's your mass, convert it to grams, convert grams to moles, and that up there is the moles of HCl. Now we need to divide moles by liters. So take your 25 milliliters and convert it to liters, and that goes in the denominator. And when you run this calculation, you get 0.008019 molarity, and remembering that the molarity of HCl, since all of the HCl dissociates into H pluses, that's also the molarity of the H pluses. So the molarity is 0.008019, two sig fig number, and this proton concentration is pH 2.1. So here is the equation which lets you calculate pH when given the proton concentration. The pH is simply the negative log of the proton concentration, or equivalently, if you solve this equation for proton concentration, it's equal to 10 to the negative pH. So given the pH, you can find the proton concentration, or given the proton concentration, you can find the pH. Now, if you're not too familiar with logs, or if it's been a while, I've made this little pH scale table, which hopefully makes it very easy to see how they're related. Suppose your proton concentration is 1 molarity. That's a lot of proton concentration. That is pH 0. If your proton concentration is 0.1 molarity, that's pH 1. So, if it's 1/10 of this, then the pH goes up by 1. Now, if it's 100th of a molarity, the pH is 2. 1,000th of a molarity, the pH is 3. Another way to write 1,000th is 10 to the negative 3. So 10 to the negative 3 molarity proton concentration is the same as pH 3. 10 to the negative 4 is pH 4, 10 to the negative 5, pH 5, and so on. And so that's how they're related. The proton concentration is the same as 10 to the negative pH. So if your pH is 4, your proton concentration is 10 to the negative 4. Now, when we go back to, say, the last problem right here, we calculated the proton concentration as 0.0080. Now, this proton concentration is bigger than 0.001, but less than 0.01. So it's greater than 0.001, but less than 0.01. So it's somewhere in this range. 0.008 is somewhere around here. So it's going to be 2 point something. So when you have your proton concentration, you should be able to look at it and at least say what the number is up here. This number just tells you what the power of 10 is. So this isn't really a significant figure, technically speaking. And that's why if you have a 2 sig fig proton concentration, this isn't counted. You go out 2 decimal points. Okay, so this is 2 sig figs, and these are your 2 sig figs here. Okay, and I guarantee you, if you plug in this proton concentration into that equation, you'll calculate pH as 2.10. So this is a good scale, and you can keep on going. 10 to the -7th is pH 7, and so on. Now, one more problem, a little more involved. Suppose you want to, or you're asked to find the pH of a solution made by dissolving 0.40 grams of hydrobromic acid in 10 liters of aqueous solution. Now, this is a multiple choice problem, and here are your choices, and you're asked to do this problem without a calculator, and maybe I should cover up this. So I just showed you kind of the answer, but just forget you saw it for a second, and see if you can answer this. So maybe pause it, and then see if you can have a go and do this problem without a calculator. Okay, so here's the solution. First, we need to find the proton concentration, and then we can calculate pH. So proton concentration, since HBr is a strong acid, the proton concentration is equal to the HBr concentration. So we can calculate HBr concentration as moles of HBr over liters of solution. Now you're told that you have 0.40 grams of HBr. We can convert that to moles, and you're told the liters of solution. So we can figure this out. You take your 0.40 grams of HBr and using its molar mass, convert that to moles, and that goes in the numerator. And then divide that by the liters of solution. And when you run this calculation, you end up with 0.00050 molarity. Now, how would you be able to do this without a calculator? So 0.40 over the molar mass of 81, you should be able to calculate the molar mass pretty easily. I'll remind you one more time on how to do that. Looking at the periodic table, the molar mass of hydrogen is 1, and the molar mass of bromine is about 80. Okay, so 1 plus 80, you get about 81 here. Okay, so molar mass is 81, so you don't need a calculator to get that number. 0.40 divided by 81, well, 40 divided by 80 is 1/2, or 0.5. And if it's 0.40 divided by 80, that would be 0.005. Okay, so if you move the decimal place over 2 spaces here, you'd have to move it over from 0.5 2 spaces there. So 0.005 is the moles. And when you divide that by 10, that decimal point comes over one more time. So 0.0005 molarity. That's your proton concentration. Now, can you tell me what pH range this lies between? Well, yes, you can. 0.005 molarity, this is less than 0.001 molarity, but it's greater than 0.0001 molarity. Now that means it's less than pH 3, greater than pH 4. So it's going to be between 3 and 4 somewhere. Okay? And there's only one answer that is between 3 and 4. The answer is C. So by process of elimination and a little bit of mental math, you can solve this problem. So you can calculate this. The pH is negative log of proton concentration. If you plug that in here, the negative log of 0.0005, you'll get 3.31. But again, to answer this problem, since it's multiple choice, you don't need a calculator. Anyway, that's it for strong versus weak acids and pH. In our next lecture, we will go into the pH of weak acids versus strong acids, and we'll focus on the pH of weak acids. And you'll see the method for doing that is by making these ice tables. So a nice calculational technique that we're going to get into in the next video. So stay tuned for that. Aloha.